let's continue. So in the last session, we just discussed some general wave equations and how wave behaves, and we separate that into. Um, we realize that the waves can have linear superposition principles, and we only need to look at one single component that have a fixed wavelength or a fixed wave number. And if we actually put that wave packet through some sort of boundary, then there can be reflected waves and transmitted waves, and this how much is being reflected depends on the velocity of these two different strings. So now let's see how the electromagnetic waves equation can be derived from the Maxwell's equations. So the Maxwell's equations we simply rewrite here in the case where there are no source. So in the here the delta del dot E simply becomes 0, and del cross B don't have the source term of J. Now this set of solutions, set of equations, you can simply say that there is two equations that are 0, and two cross equations. One is the Faraday law, another is the Maxwell's correction to the Ampere's law. So there are four equations, and we can actually apply del cross to each one of them, and this will actually help us decouple the equations. So right now you see that the electric field, in order to get the electric field, you have to know the B field, and in order to get the B field, you have to get the E field. So now what happens if we apply a del cross on each of them? So say that if we want to apply a del cross on the del cross E, then we have this identity of the second order differential to the term over here. So the first term del dot E is exactly 0 because the first identity, and the second term, so that also only left the second term. Now the del cross E, we can replace that by this del cross partial B partial T, and let's put this partial T outside, and then we get a del cross B. So the del cross B is can be written as a partial E partial T again. So in the end, we can express the minus del cross E as minus mu naught epsilon naught partial square E partial T. Likewise, we can do the same expression for the B field. So the first term equals to exactly 0, and then only the second term left over, and the del cross B, we change that to partial E partial T, and then we pull the partial T outside, and the del cross E gives us back to partial B partial T. So for this B field, we also have the similar equation. So you see that now after we do a del cross, the first function only involves the E field, and the second function only involves the B field. But the function E and the B base are exactly identical to each other. So that is the wave function for the electric field and the magnetic field. So now if we rewrite this wave function in terms of this 1 over v square form, and we can calculate the speed of this wave function should be 1 over square root of epsilon naught times mu naught. And this is actually exactly the speed of light, which is 3 times 10 to the power of 8. And the thing that we want to notice, that which is different from the previously one-dimensional wave, is that here this is E is a vector and B is also a vector, which means here each component of the E obeys the wave equations. So you should think of this as a three-dimensional wave, and instead of wave that's only along the x direction, there are actually three components. You have to think of them. Think of this equation as each wave equation for each component. Now, for the simplest case, we can define monochromatic plane waves. So what I mean by monochromatic is each frequency can correspond to a color of this wave. So then that fixes the frequency. And what I mean by a plane wave is that the wave function only travels along, say, the d direction, and the E field doesn't have any x and y dependency. So this is one of the simplest case of a wave, and this is called a plane wave because here the wave equation along the x and y has a translational symmetry. So the wave function doesn't depend on the coordinate of x and y, and it's only fixed by the momentum or the transmission direction along the d direction. So for the plane wave, it has make use of the translational symmetry, and sometimes in graduate level courses, we might come across some spherical waves. So for a spherical wave, it's different from the plane wave in the sense that it actually travels along the radial direction, and this one makes use of the rotational symmetry of the problem. So, but again, you can still transform the solution in plane wave to spherical wave and backwards. And this you can think of this as simply making a unitary transformation and going from one set of bases to another set of bases. But you won't come across this until graduate school, I guess. So for plane waves, we can write out our field, say for the electric field, as a complex. So here I already casted them in complex forms. So the complex E field along the propagating along the d direction can be written out as a complex amplitude and a vector. And also similarly for the B field, we have a complex amplitude vector, and multiplied by this kz minus omega t. So here there is only one single k and omega because we are looking at a monochromatic wave, so there is only one frequency of light. So here, because the speed of light for is fixed, so k and omega has a fixed relationship. So the omega is the angular frequency, and it's equals to the speed of light times the wave number. So remember that the units for this frequency is 1 over second, and the unit for the speed of light is meter per second. So the unit for the wave number k is 1 over meter. So you can double check your unit for the k by looking at kz. So here this phase factor kz minus omega t must be dimensionless. So because z has a unit of meter, so k must have a unit of 1/meter. So this relationship in terms of units actually makes sense. Now the wave. So here right now we know that the Maxwell equations claim that they base some sort of wave equations, but not only they are wave, but they are some sort of particular types of waves, because we know that the divergence of E and the divergence of B must be exactly 0, and likewise we know that the imaginary part of this complex E and B also obey the exact same relationships. So now if we combine the real and the imaginary part of this E field together, the complex function of this E and B also obey the exact same rules. And now what this means is that if we take a partial derivative along the z direction, this one has to be along the z direction has to be exactly 0. Otherwise, because we can see that the second one actually generates a constant, generates a function of k exponential of I kz minus omega t. So this function cannot be 0 unless this amplitude in front is 0. So this means the amplitude here along the z direction must be exactly 0. Otherwise, this divergence is not 0. So this means that the amplitude of the wave cannot be along the direction of propagation, and this means the electromagnetic waves must be transverse waves. So remember we talked about the transverse and the longitudinal waves in the previous session. And we also have additional requirements, that is the Faraday's law. So del cross E must be related to the minus partial B partial T. So here the amplitude of this E wave and the amplitude of the B waves must be related to each other. So say that we write out explicitly this curl operator, then that relates the y component of the E field to the x component of the B field, and the x component of the E field to the y component of the B field. So remember here, these are all discussing the amplitude of this complex amplitude of this wave. So we can compactly express this relation using the cross product. So what this means is here say that we are looking at a wave that's propagating along the z direction, and now say the electric field is along the x direction, then the B field must be along the y direction because of this cross product. So we've already also, I believe we have learned this from the physics 2041. So for propagating light wave equations, the E field is perpendicular to this propagation direction z, and the B field then also must be perpendicular to both of them. So here the B is that is because the B is Z cross the direction of the E. So in this case, Z cross X equals Y. And not only this determines the direction of the B field, it also determines the amplitude of the B field. So now say that the x, y are all perpendicular to each other, then this means the amplitude of B must be equal to the k divided by omega times the amplitude of the E. And k and omega, so k is in the unit of 1/meter, and omega is in the unit of 1/second. So the unit of this is second over meter, and this constant is actually the 1/speed of light. So now you see that the amplitude of the B field is actually the amplitude of the E field divided by the speed of light. So in typical situations, we consider the electric field of the light to be much more important than the magnetic field of the light. So say that if we shine some light to the atoms, so the atoms can feel both the electric field and the magnetic field of the light, but the electrical effects are much more important than the magnetic effect. So only as the cases where the electric effect goes to zero, we have to consider the magnetic effect. And you might come across this in your research, I guess, later. Say if you are looking into the either the theoretical side of AMO physics or some experimental side of the AMO physics. So typically, when we express the wave functions of light, because the electric field is much more important than the magnetic field, we typically use only express the E field explicitly, and you have to derive where is the direction of the magnetic field by taking this cross product of Z cross E. Now, say that for example, if I guess that I have already talked about this example. So here, this is the explicit expression for what I just talked about. So for electric field that's pointing along the x direction, then the B field must be exactly along the y direction. So in terms of the complex numbers, the electric field goes as E tilde times I kz minus omega t. And for the B field, it must be E tilde over C. So this is amplitude is slightly different. And also the direction is changing from x direction to y direction. Now, what in reality what means is we are looking at the real part of this complex functions. So we have to take the real part, which gives us E naught times cosine kz minus omega t plus the delta. So here, remember that this E naught is delta is E naught times e to the I delta, and we have to bring this delta back here. So if you plot the wave function, this is how the wave function should look like. So here the E field is always oscillating along the x direction, and the B field is always oscillating along the y direction. So for this linearly polarized light, or when the polarization vector is always fixed by when the light propagates, the B field and the E field, you can see that they are in phase. So that might not be always the case. So the light does not simply take the linear polarization, such as the along the one fixed direction, but sometimes you can actually having circularly polarized light. So you can imagine that one light, the polarization angle is rotating as the light propagates, and there are just like the polarization in linear polarization in x and y coordinates. You can also write out your circularly polarized light into two different types of polarization. One is right-hand circularly polarized light. Another is left-hand circularly polarized light. So these two lights are orthogonal to each other, and in fact, you can either choose the basis of linearly polarized light, or the basis of two circularly polarized light, and you can write down the you can do a unitary transformation between these two type of bases. Um, you might we might have additional homework, and that should be one of the homework problems, is to look at how the light polarization can be write down differently in terms of the left and the right hand circularized polarized light. So before we talk about the light propagation only along the only along the z-axis. So we write down the propagation as e times I kz minus omega t, right? But and we can actually rotate any axis to the axis of propagation, put that to the z. But we actually can also have a more general form of expression. So instead of writing down as kz, we can also write down as the e minus I times kx times x plus ky times y plus kz times z minus omega t. So this is a general wave function in arbitrary direction. So now instead of this complex notation, we can simplify the notation by the k dot r. And what here, then you can see that the direction of the k actually points the direction of the propagation. So now if we set k to be 0, 0, kz, then this goes back to our original case of propagating along the z direction. So writing the result down as k dot r doesn't make the things more complicated, but it actually generalizes the light propagation from the z-axis to an arbitrary direction of k. Now, after you write down the propagation vector k, you have to be aware that here we have a polarization vector, and this polarization vector cannot have an arbitrary direction. It has to be perpendicular to the direction of the propagation, which is k. So the dot product of the n and the k must be exactly 0. Now, if we explicitly write out the real part of this complex functions, then the real part should be exactly equal to the e naught times e to the we have to take the real part of this expression, and the real, before we do that, we need to write out the E tilde, remember, as the E naught times e to the I delta, and then put the delta to the end of here, and then we have the real part as E naught times cosine kz minus omega t plus the angle here, by moving that back. And similarly for the B field, we divide the amplitude of E naught by speed of light, and we need to also change the direction of the polarization to k hat cross the n hat, which gives you the other axis that's both perpendicular to the light polarization and the light propagation. So next I will briefly discuss the energy and the momentum of the light field. But you have already seen this part in the physics 2041. So I'm not going to too much depth here. So first we want to have an idea of what's the energy of this plane wave solutions. So we have calculated the energy of the E field and the B field before. So if you still remember that the total energy of the E field, it looks like the three-dimensional integral of epsilon naught E square integration over the whole space, and the magnetic field energy is 1/2 1 over mu naught times B square over all space. So these are the solutions in vacuum. But now let's look at what I mean by the mu here is simply what's inside the integral. Sorry, I should actually. So integrating over the mu gives us the total electric energy, and integrating the mu b gives us the total magnetic energy. So this mu is the energy density, which has the unit of energy over the length cubed. Now, if you calculate that energy by combining the electric field energy and the magnetic field energy, so what we have is for monochromatic plane waves, the B square, remember the B is E naught divided by C. So the B square is E square divided by C square. And if you still remember the expression for the C, so the C is square root of mu naught times epsilon naught. So we can rewrite 1 over C square by mu naught epsilon naught. And then what if you multiply this factor into the expression over here, we actually see that something interesting happens. So the first term is actually exactly identical to the second term. So for light, the electric energy and the magnetic energy actually contribute equally to this energy density mu, U. So we can simply express U as epsilon naught times E squared. Of course, the amplitude of the E squared explicitly written down should be as the amplitude E naught squared times the cosine kz minus omega t plus this phase constant delta. So you can sort of imagine that in the space, the as the light passes through, the energy density actually oscillates as the cosine theta square. And now say that we put one right propagating light together with one left propagating light. We can actually make the system a standing wave. So for one example of a standing wave, so the standing wave solution would be looking like here. So there won't be any time dependence. Or you can think of this as a snapshot of the energy density at a specific time moment t, right? So for this kind of wave, it's actually interesting in the sense that the energy distribution inside the space is not constant. So it actually oscillates up and down. And now, if you look at your microwave at your home, what microwave is also producing a wave solution, and the wave inside of your microwave is a standing wave, like the expression that I wrote down. So you see that the energy inside your microwave is not a constant through all your space. So that's why in your microwave you have to rotate your plate. Otherwise, say that if you take your plate out, you can see that the temperature is not even, and so there are also some experiments on YouTube that you can, based on the parameters on your microwave, if you put a pie inside and don't rotate, based on how hot your pie become, you can actually deduce the speed of light from the temperature distribution of your pie. So of course, to know that, you have to know the frequency of your microwave. But for all the microwaves, the frequencies, operating frequencies are always on your back. So you can check at your microwave at home. So for the now what we have here is the energy density. So the energy in unit volume, and not only the energy is carried by the wave, so it actually has an energy flow by this wave. So you can sort of imagine that if you calculate the energy per volume, that gives you the energy density. But if you calculate the energy flux per area, you can also get a pointing vector, and this vector calculates the how many energy has passed one unit area at a given unit time. So you have to be careful. So this is the definition of the energy flux density. So it's the energy per unit area, so per length square, and per time, so t. Now this quantity is given by the pointing vector. So remember that say that we have a electric field along the x direction, and we have a magnetic field along the y direction. Then the propagation direction is along the z direction. And for this case, the pointing vector is x cross y is equal to z. So the pointing vector is actually along the direction of propagation, and that pointing vector gives you how the energy flux is traveling. So for the plane wave that's monochromatic, then the Poynting vector is exactly along the direction of traveling, and the amplitude gives you the total energy flux density. Now from this total energy flux density, we can again do a slight calculation and get the momentum density stored in the field. So I'm not going to derive this, but I'm going to give you the check on the units. So remember that the S, that is E, divided by the length squared t. And now if we multiply that by 1 over speed of light square, so which is t squared divided by L squared. So this gives us E times T divided by L to the fourth. So now we can separate this terms by T over L and L divided by L cubed. So the T over L is velocity, 1 over velocity. So now energy divided by velocity gives us the momentum. So the first term is momentum, and the second term is the unit volume. So momentum per unit volume. So that gives us the G as the momentum per unit volume, which means the momentum density. So the momentum density stored in the field is simply S divided by C squared. So you see that both the energy and both the energy flux density and the momentum density is proportional to the Poynting vector S. So that's because the dispersion relationship of light is different from a mass particle. So for a mass particle, the energy is p squared over 2m, and so you can see that this is a quadratic dispersion. And so you imagine that the energy as a function of p is a parabolic like this. But for light, the energy is only linearly proportional to the frequency omega. And you can sort of see that the energy as a function of momentum for the light is actually linear. So the larger the expected momentum, then the larger the energy of that light photon is. So say that if you are kicked by a photon, then the energy transfer is h bar omega, and the momentum transfer is also linear of h bar omega. What's the momentum transfer? So the p should be h bar k. Right? Is that correct? I guess that should be correct. Which is E over C. So the difference between momentum and the energy is a factor of 1 over C for a light. So for the light, the dispersion relation of E over P is a straight line. Now, if we take a look at the, so previously what we discussed is the instantaneous momentum density, or instantaneous point vector, and um, energy density. But because the light has actually a typically fast oscillating frequency, so we sometimes are more interested in the average energy, or the average Poynting vector, and the average momentum density. So that can be done by integrating the wave function by one period of time. So now if we integrate the cosine square function over one period, that gives us simply 1/2. So we can do the calculations straightforwardly for all of the quantities by replacing the cosine square by 1/2, and that gives us the plane wave solution, the simple solution like this here. So from here, these quantities are much more physical to observers, that is insensitive to the phase of the light. So the average of the energy carried by the electromagnetic field is simply proportional to this epsilon naught E naught square, and the Poynting vector, you need to add some constant speed of light and fix the direction along the direction of the propagation, and then for this momentum density, you need to divide the Poynting vector by c square. So physically, what's the meaning of all these quantities? Well, first we can relate the Poynting vector to the light intensity. So the Poynting vector, so the average Poynting vector is actually the definition of the light intensity. So from here, we immediately see that the light intensity is given by the electric field amplitude square. So that is related to the how much power your light can give per unit area. So so here, remember that the Poynting vector is the energy per length square per time. So energy per time gives us the power, and the length square is the area. So the unit of this Poynting vector is the power per unit area. Now, not only we can get the light intensity, we can also get the momentum kick by a electromagnetic wave. So say that we have a wave that's being absorbed by a perfect absorber. So a perfect absorber means that after a photon hits the wall here, the photon will be entirely absorbed by this wall, and it can turn into thermal energies, and there won't be any reflected light. So for this type of perfect absorber, you can imagine that the momentum of this photon, which has a p, which is remember that that is proportional to E over c. This kind of momentum is being transferred to the observer, and then the total amount of the momentum transferred by the observer can be given by delta p. So I'm not going to derive why that's the number, but I'm also trying to check if the dimension of this quantity makes sense. So let's see. So the G is in units of momentum per length cubed. So here the G is a momentum per length cubed, and now I multiply the by length squared, the area, and multiply the speed of light, and then I multiply by t. So see that here the t cancels, the area cubed cancel with the so the length cubed cancel with the area and the length. So you see that indeed the delta p has the unit of momentum. Now because delta p has a unit of momentum, then the momentum, if you take the derivative of momentum with respect to time, that gives you so momentum is m times v dot, and now m, which is sorry, the momentum is m times v, and if you do an extra derivative with time, then that's mv dot, which is ma. So here the delta p delta t is simply equal to the force. So the force per unit area actually give us the pressure. So unit-wise, this must make sense, right? So now if we plug everything in, then we see that the pressure, a perfect absorber field is simply the intensity divided by the speed of light c. So by the way, the I here, the intensity of the light, also means the average power heating on this wall that's being absorbed by this perfect absorber in unit time. So you can think of that this absorber not only absorbs the energy per unit area in this amount I, it also this amount also gives it some momentum forward. So this absorber can get the energy and get some pressure. So now let's take another case, which is instead of perfect absorber, we can have a perfect reflector. So what I mean by a perfect reflector is the light is not being absorbed by the mirror at all, but this mirror can reflect the light 100%. In this case, you can imagine that the photon not only give it a kick to the right, this will also have to emit a photon to the left. So there are twice of the change of the momentum. So the radiation pressure on a mirror must be twice as large as on a black body or a perfect absorber. Okay, so this is the end for today. So next time we will discuss how the light transmits in the boundary of two different media. So it's similar to the propagation of light into two strings with different mass. So we will see how the light passes through different media and how it's transmitted and reflected is actually almost exactly the same as the stream wave propagation on a string.